Okay, it's 4 o'clock, so I think we should get started. I'm Nawajish Noman. I go by Noman, that's easy. And my colleague Deng here. We'll be talking about working with multidimensional scientific data, right? It's kind of a loaded word, but let's see if we can demystify it, and then I'll tell you what we're going to talk about. And at that point, if you don't like it, that's okay. You can find a session that you like, but if you find it interesting, stay with us and we'll go through it. Okay, so what are the things we're going to talk about? We're going to talk about scientific multidimensional data. What does it mean to us, right? Because the scientific word is like everything we do scientific, so what's up with that? Multidimensional is another overloaded word, but then when we combine these two, we actually mean something different. So we'll see how does that go. Then we're going to talk about how to ingest that data, simple word, how to read that data in ArcGIS and how we manage it, right? Then we're going to talk about analysis and visualization, because we're in a GIS system. If we cannot see it, we cannot understand it. If we see it, the next thing we want to do is we want to analyze it, right? Otherwise, what's the point, right? And then, of course, there will be a point where you say, guys, you did not build enough tool for me. Those 1200 analytical tool is not good for me. I need 1201. So I want to write my own tool, right? So that's what we're going to talk about. And then finally, is that we have done all the great work. How come I cannot show it off, right? I want to share with my colleague, other organizations. So we talk about sharing and web application a little bit, right? So let's get started. Right. Let's clearly define what we mean by scientific multidimensional data as far as I am concerned and Deng is concerned in this room. We're talking about something called netCDF, GRIB, and HDF format. Is any of you familiar with this data set? Some of you. That's a great sign, because a lot of observed data from satellite, if you use NASA data, chances are strong you work with HDF. If you work with some model result from NOAA or some other places, you may have worked with netCDF or GRIB. So it's there. And some of you may have used this data which has been converted to shapefile or something else, raster, but it probably originated from one of these formats, right? So, and they are multidimensional in nature. What does it really mean? That it varies with time and it varies with altitude or depth in the ocean, more than 2 dimensions, right? So that's my premise, right? That's what we're talking about. So what are the examples of those kind of data? Some ocean data, sea surface temperature, salinity, ocean current, and of course, ocean is a big 3D thing. Weather data, again, temperature, atmosphere, whether it's a model result or observed data. Land data, soil moisture, land cover, NDVI. So the examples goes on, and you may have encountered this data one way or the other, maybe not it's in original format that it was originated, but in some other format. But in this case, we're going to talk about the original format. Now, before we go down that line, we always have to talk about our ArcGIS platform. Why? Not because all of you are using that in your day-to-day work, but it is important that you see how these things are fit together, right? So in plenary and everywhere we talk about our ArcGIS platform. To some of you, it's a desktop, web, some other devices. It's an ecosystem, right, where you have online services as content sitting on a server, serving information from other places, you are consuming it, or you're just working by itself here. Whatever your scenario is, the idea is whatever I'm talking here is applicable to this entire ecosystem. It's an environment. You can work everywhere, right? What are the things we want to do? When we start working on this, and back in 9.2, that is the first release when we actually exposed this functionality, we had a very simple vision. The vision is those unknown looking data format that is not considered as regular GIS data, we will treat them like a GIS data. We'll make it easier so that people can read it directly without any conversion. Very simple vision, right? That means you will be able to do everything that you do with your traditional shapefile, FG, feature class or raster. You should be able to do those things with this data. That's the vision. So if you look at it, actually, starts from direct ingest, direct reading, no conversion. Number one, you should be able to manage that data in our system. You should be able to visualize it, should be able to analyze with it, share with other people. That the cycle goes on, right? So that was our vision, and we are still working through it, and we'll show you today how much we have accomplished and where to go next, right? So how do we ingest scientific data in ArcGIS? Now I'm gonna kind of go a little faster here. There are many ways we can go about it. If you're talking about netCDF tool, you can actually use this toolbox called multidimensional tool, and there are a bunch of tools, and some of the tools starts with the word make. There you go. That means you can use those tools to create something. Things that you can create is either raster or a features or table. You can also use this OpenDepth service tool to ingest OpenDepth services. Some of the organizations actually publish data through OpenDepth services. NOAA is doing that, many organizations doing that, right? It also supports subsetting. Then you can also manage and put this data in Mosaic and ingest it through that. So our Mosaic Dataset, if you're familiar, anybody familiar with Mosaic Dataset here by any chance? Some of you. We'll talk about that more detail down the line. Supports netCDF, HDF and GRIB. So you can put it in Mosaic, then do stuff with it, or you can read it directly and do stuff with it. That's the whole point, right? There is also easy dialog in Pro 2.1, which actually let you read multidimensional raster layer. So if you, it's like from add data button, you choose that option, not this one, I said later. So you choose that option, that brings up that one, and you select your variable, you select your file, you select your variable, and there you go. It just do it for you, right? You don't have to run a geoprocessing tool. Okay. Okay. Now that we talk about how we ingest it, there are something we have to tell. If you are familiar with this data, you know that this is very powerful. That means you can write things in a many different ways. That is a good thing. That is also a problematic thing for us, because we need some detection when we are opening that file and trying to make sense out of it. So what we do, we actually rely on CAF convention to do it. That means if you have written your file following CAF convention, we can read it. Otherwise, good luck, we have to have discussion, right? That's the whole point of saying that, right? Because we can't just randomly read file and make sense out of it, because it's very flexible. Now there is another thing, another key reason why we actually chose CF convention. We are in a GIS system, that means it has to have special reference. We have to put it somewhere on Earth, right? And we cannot do that if we don't have special reference. Which convention prescribe the special reference well? CF. Through grid mapping, it actually tells you, and we can read data in geographic coordinate system, we can read data in projected coordinate system. We know how to read that by looking at the convention and do it, right? Then what about the aggregation? Because some of these files comes in pieces. They are not, if you look at an HDF file, you may see only one area. Then you have another file in one area, another file one area. But you want to see the entire ocean, well, entire world, right? How are we going to do that? Or you have files that are, one file in one time step, another file in another time step. How you want to see it as a cube, right? Because those are all single slices. You want to see it as a hypercube, a 3D cube or 4D cube. So to solve that problem, we said, you know what? We can do that if you put it in a Mosaic dataset. Because Mosaic dataset actually had that capability with raster. So we enabled Mosaic to support this format. Now if you put it, you can see it as a cube, a hypercube, right? And you can use that to do that. But the moment we did it, we also unleashed other power, because Mosaic Dataset had a lot of other functionality that we're using it for regular raster. What are those things, right? After we did it, you can do spatial aggregation, temporal aggregation. Most importantly, you can do on-the-fly analysis. Some people were talking about raster function, and we'll talk about that a little bit more later on. We can also serve this data as image service, map service, WMS. What it does for us, it supports data ingest, it eliminates data conversion, eliminates data processing, improves workflow performance, and integrates with service-oriented architecture. That means entire platform, right? So, and Deng will show you some of it. How to create a mosaic? Simple. You just have to know the product type that you're using, and you specify the form type, netCDF, HDF, and GRIB. If you want to apply any other processing template, right, vector field or some other unit conversion, you apply that, and there you go, it creates. With that, I'll hand over to Deng to show you some of these things in action.
Can you hear me? So first, I'd like to show you how to ingest netCDF files. We have this multidimensional tool set. You can use make netCDF raster layer, feature layer, or table view to ingest netCDF files. Let me introduce the parameters of the make netCDF raster layer. If your variables in the netCDF file is contiguous and regularly spaced, you can use it in this tool. You input the netCDF file, and then all the variables will be automatically populated. You select any of them of your interest, and the XY dimensions will be automatically populated. You give a name of the layer, and there's one parameter that is optional, which helps you to select any slice of the dimension. Let's run this tool. We can also automate this by using Python snippet. If you open the tool help, you will see this example code of using this tool in Python script. Another way of doing that, to know the syntax of the Python, you just go to the history and send to Python window from your tool history, and then you will get the syntax of this tool. If the variable inside your netCDF file is station data or irregularly spaced, you can use make netCDF feature layer. So input this file, and similarly all the variables will be populated. For netCDF feature layer, you actually can select multiple variables as long as they share the same dimension. One of the important optional parameter is the row dimension. You need to specify one of the row dimensions so that you will see more than at least one records in your netCDF feature layer. For here, I'm selecting profile. Let's run this tool from the history instead, using the Python. Zoom to the layer. As you can see, this is the underwater glider data, and it shows the path of the underwater glider measurements. When you open the attributes table, you will see the salinity and time field and all the values. There's another way of ingest scientific data, multidimensional scientific data. which is to use multidimensional raster layer. As long as you input the file, it will populate all the variables inside it, along with the dimension size. So you can select any of these variables and choose the output configuration. The first one is multidimensional raster. So the output is AFR, which is ArcGIS functional raster. And then the second one, classic netCDF raster, is actually the same as the make netCDF raster layer 2. Here's this water temperature layer. If we have multiple netCDF files or scientific files like GRIB or HDF files, we want to manage them using Mosaic Dataset. For example, I have this HiCom data downloaded from this website, and I downloaded region 1 and region 7, and for 3 time steps. So there are 6 files in my folder. I want to spatially and temporally aggregate them. To do that, I will need to create a Mosaic dataset and then add rasters into it. So let's take a look at the Python script tool, a Python script. Let me get to presentation mode. So in this script, I have 2 steps. First is create Mosaic dataset, and then second is to add rasters. Let me run this tool. As it's running, let's take a look at the input parameters. The required is the GDB name, the Mosaic dataset name, and the spatial reference. And then second step, adding rasters, you need to specify the input Mosaic dataset path. And one important thing is the raster type. You can specify netCDF, since I have netCDF files, or you can actually specify a .art file path. So in this way, you define the variables and processing templates in this file. So you customize your variables in the Mosaic dataset. If you specify netCDF, it will actually add all the variables in the netCDF file into the Mosaic. So here I run this script by specifying certain variables. Let's take a look at the result. Refresh this FGDB. As you can see, I actually only select water U and water V component variables in this netCDF file and use a vector field processing template so that it only have 2 variables inside the Mosaic dataset. And they are composed as vector field. For the netCDF file type, you'll actually see all the variables here. That's how we ingest and manage scientific data. Back to you, Norman.
Thank you very much, Deng. Number 3. Okay, so we talk about how to ingest scientific data through dialog, through geoprocessing tool, and another important thing was if you have too many files, how you manage them and actually present it as a seamless layer through Mosaic, right? Now that you have brought those files in ArcGIS and Pro, what are you going to do with it, right? Of course, you want to display it, and when we say display, we mean many things, and we'll come to that, but you want to display them, and all the other display functionality that we have, it actually works on them. You can also create a chart and stuff like that. You want to animate so that you can see how things are changing either in time or in altitude or in depth in ocean. You can do that also. You can also do analysis. Now somebody said, hey, your multidimensional tool is only few tools here. How can I do analysis? The reason we can do analysis is because when we actually ingested it, we ingest it as a raster or feature as a table. So all those other tools that we have that actually works on raster, feature and table also work on this data. That's how you can actually do a lot of analysis that is not obvious sometimes, right? We'll talk about that a little bit more. Let's talk about the visualization, right? So in visualization, we want to do slicing. Slicing means, as I said, change time step, see something different, not the first one, the third one, the fifth one, or whatever. Change depth and stuff like that. For temporal animation, you can use the time slider. Any of you are familiar with time slider by any chance? Some of you here. So that's a great thing, right? You can just use it to animate it, or you can go step by step and see things, right? Something is called range slider. Anybody familiar, heard of that thing? Again, a few people. That's actually a cool thing, because if you have a dimension which is not time, like depth or something, or you want to see a different story of the house, or you want to constrain the value that you're looking at, you can actually use range slider to do that. So it's not only for this data, for all other data, these things are actually relevant, right? And if you are working with some kind of velocity or current, like, or wind speed, right? And you want to see them. How you can do that? You can actually do that using predefined renderer like vector field. We'll talk about that a little bit more. How do you change time slice, right? There are many ways to go about it. Of course, time slider is the obvious one, but there are few non-obvious ones, but equally important. For example, you can, in 10x, in ArcMap, you can actually go to the layer property and change the time step. You could have actually done it on creation, and Deng mentioned that there is a, at the bottom of the tool, there says select the dimension value. You could change that there too. But obviously, you will probably create with the default one, but then you want to change it, so you can go through this step. Then there is another tool called select by dimension that let you change the slice, right? Any way you want. I want time, 10th time, and 50th depth, and you can do that, right? Okay. So here is the animation slider that you actually go through and specify your inputs over there, and then you can actually set the layer properties, and then you can just use the slider to either step through or animate each time step. Similarly, you can go and use the range slider, where again it's a similar concept. You say, hey, for this layer, I'm going to use range slider. You just specify whatever you are trying to animate through, and then you just use the slider to do it. And obviously, we did not put it at the top because top is the time slider, and then for depth or altitude, it made sense to do a vertical slider. So that's a vertical slider. You can have both up and running at the same time. So you're moving through time and depth and looking for the stuff that you want to look for, right? So that's actually great data exploration tool, right? So if you want to see how things are changing, you want to use this tool slider to actually look at your data. Then visualization of raster as vector. Has any of you worked with wind speed or ocean current? You may, I see some hands in the behind. The interesting fact is, sometimes this data come in U and V component. Sometimes they come in direction and magnitude component. And in most of the cases, it comes like a raster, it's a gridded thing. But that's not how you want to see it. You want to see it with nice arrows, and then you don't want to see all the arrow at the same time, right? So that poses a challenge. How do you do it? Earlier, people were converting them and then using point symbol to do it, and then resampling it and writing their code. That was a laborious process. It did not work out for NOAA. It did not work for Navy. and we understand the problem. So what we did now, we created this renderer which creates this kind of arrow dynamically on the fly. And what you can actually do, you can specify how many points you want to see. As you zoom in, you'll see more points. Zoom out, you'll see less point. And when it's zooming out, seeing less point, what kind of resampling going on, you can specify all of these. That way, you can actually see this information much better, right? Now going back to analysis, I said that we can do a lot of analysis. Why is that? Because we have all these tools in this toolbox and works with feature and raster. You can put them together and solve a complex problem, right? And you don't need a specific multi-dimensional analytical tool to do that. You can do that by combining all these tools that you already have. You can also do on-the-fly function processing. On-the-fly analysis. We mentioned that when you do Mosaic, you can actually apply those functions. And what is the on-the-fly processing here, right? On-the-fly processing means we're not going to create a new data set, right? So sometimes if you look at the temperature, the data, if you crack open, it is in Kelvin. So who knows what is the temperature now in Kelvin? Who cares, right? You want it in Fahrenheit. Come on, right? You don't even want it in centigrade, or maybe you do. But obviously not Kelvin to understand, I'm going to bring my jacket or not. So are you going to convert that data? It's a simple equation. You don't have to do that. You can actually build a simple function chain and apply dynamically on it. So even though your source information is in Kelvin, but your output product information can be in Fahrenheit or centigrade. So this is the power of doing on-the-fly processing. And another important power is actually you can combine two different variables and create a completely new product like wind chill, right? And you don't have to save it on disk. People also use Python to actually expose and do some other analytical tool, expose other functionality. Here's an example how we use Python to actually do some new tools, right? Here is an example where we did some very specific thing for NextRad, right, or edge detection. So my point is, when you don't find the tool in the toolbox, go and use Python, and somebody wrote some cool function, you just expose it through a tool, and there you go. You can perform the analysis you want. Many organizations has done a lot of this thing, like MGate is one of the very well-known tool set. They have hundreds of tools they have written, and they do lots of good work. Australian Navy has written a bunch of tools, of course not openly available, but I know they have done it. Even ourselves, we have used Python to write tools, like we create space-time cube, that actually create a multidimensional cube written in netCDF. And then we have used that in emerging hotspot analysis to actually display it and view it. So bottom line here is you can use Python package, which is already part of your installation, netCDF for Python, and interact with this kind of file and perform a lot of new different things, new different analysis with it. And you can also use Python to write Python raster function, which you can attach to a service on the server end, and actually you can get those kind of analytical result on the fly. With that, I'll hand over to Dave.
Thank you, Norman. After adding your netCDF raster or feature into map, you want to take a look at how your data looks like, maybe through time. We have this underwater glider data. It's this path, and we want to know how they move throughout the days. To do that, we can enable the time field of this data. And these data time extent are automatically populated. And then you can enable the time slider. And you may want to change your time span as day to see how each day they move. Oh, that's 3 days. That's fine. As you can see, they are now moving through time. In Pro, we also have another visualization, which is range slider. For this HiCom data, where's my data? Oh, I should disable the time. Yeah. The HiCom data has the depth dimension. For here, as you can see, it's now, say, the standard Z, which is the depth, equal to 0. That is the sea surface. And you can enable the range slider by going to Map Range and specify the standard Z as the range. And you can move through the range slider to different depths to see how your data looks like. This is the water temperature. Sometimes you may also want to explore the data by profile the temperature. For example, this HiCom water temperature data, I have some specific location. I want to make a chart about the temperature profile. We can do that by using a sample tool. Input this HiCom water temperature mosaic layer as the raster, and then you can select any location on your graph, on your map. And then for checking this process as multidimensional, you will sample through all the time values. The output is a table. In this table, you will see at this particular location, all the temperature values throughout the dimensions and time. You can right-click on the chart, on the table, and then create a chart. For here, I use the scatter plot chart. And the axis as water temperature, the Y as standard Z, so that you can see there's a water temperature profile. After visualizing your data, you may want to do some further analysis. For example, this is a monthly maximum temperature data from a netCDF file. We actually want to know it is a long time series. Let's bring out the Make netCDF raster layer tool. Okay, from here. This one. Okay, maybe select by dimension tool. As you can see, this is a long time series and it has monthly data. So what I want to do is to generate a raster layer that represents the average of the June maximum temperature throughout all the years. Let's take a look at the script. First, let me run this. As it's running, let's take a look at how we are automating this workflow. So first, we need to create the netCDF raster layer from each of the year. So this part is actually from the Python snippet from the help doc. You just modify the input netCDF file, the path, the variables you are interested. And here you have a loop throughout all the years from 1895 to 1993. So for each of the year, you are make netCDF raster layer. And by specifying the the dimension values for time, you are actually making the netCDF raster layer for that particular month and particular year. Then you put all the layers inside a list. And this list can be used as an input into cell statistics, which is a spatial analysis tool. And then you specify the statistics as mean so that you calculate the mean of all the June maximum temperature. The script is still running, but I have pre-run this so we can take a look at the result. So this is the result I got from the script. This is the average June maximum temperature for all these years. We can extend the ArcGIS analytical capabilities by using Python Scipy stack libraries. As you know, there are a lot of libraries that are very powerful, such as NumPy and netCDF4. So here in this demo, I have this netCDF raster layer represents the precipitation. It has a time dimension, and I have these watershed boundaries. In Spatial Analyst, we have a tool called zonal statistics, so we can calculate the statistics for each of the watershed zone. However, that is based on for each of the pixels or the grids of the raster, when they intersect with the polygon, the assumption for that tool is they contribute equally to that polygon. So I actually want to compute the statistics based on some weights, which is the area of the intersected polygons. The areas are different. So I want to weight that to calculate the statistics. I actually have a Python script tool for doing that. It is called area weighted zonal mean. I gave it the name. So you can specify the raster layer and the input zone. When you select the process time dimensions, it will actually calculate the statistics for each of the time within this time range. So let's do the calculation. And then I will explain the Python script. So the tool is actually a PYT file. And in this PYT file, there's a template you can utilize after you create a toolbox. So this template has this toolbox class, and you can customize the tool class in it. So here, this area weighted zonal mean is my customized tool. In this tool, I define all these input parameters, and I check the license. Since I use some spatial analysis tools like Sample tool, I check if the extension is available. And I also put some customized tool parameter validation. Then the main part of this tool is first I use the minimum boundary geometry tool to create an envelope of the input zone polygons. And then I use that to create a fishnet represents the raster grids. Then I intersect the fishnet with my input watershed zones, polygons. And then I calculate the the geodesic areas for each of the intersected polygons. Here there's a if-else statement. So if the time dimension is checked, that means we want to process for each of the time step. In that, I'm using select by dimension tool to select to the specific time slice, and then use sample tool to sample that values for each of the fishnet center. Then I'll calculate the total geodesic area for each of the zone polygon, and then calculate the weights, and using the weights to calculate the average of these raster values, of those values. Then finally, I create polygons and append those mean values to the polygon feature class. Let's take a look at the result. So the result is still a polygon feature class. Since I have 2 time steps within this time extent, then the result will have 6 polygons. And there's a mean field, that's the area weighted zone of the precipitation. And there's this time field. So that's how we extend the ArcGIS analytical capabilities by using Python script tool. Back to you, Norman.
Thank you. Let's see. Before I go on and start talking about sharing and everything, let's recap for a second what we have just seen. Right? Deng has showed you, many small demos starting from visualization, creating graph, but things got really excited towards the end where she was doing a very interesting analysis for different temperature, different month, and all these things. But if you look at our toolbox, you will not see any tool that immediately says that you can do those kind of things. But she was clever enough to look at the cell statistics or some of the tools that we have already in the toolbox, and then position your data correctly and apply those tools to answer a very complex question, right? So that is the power of putting all these tools together to solve an analytical problem, right? And then in the next example, she actually went outside of our out-of-the-box tool. So she mentioned that you want to do a zonal statistics, you want to find some kind of average within that area. However, you don't want to use all the cells and get the value from the cells that are partially covered. You want to compute the statistics based on the partial value, right, based on area. And she wrote some script to actually do that. That means some operation that cannot be done immediately, with out-of-the-box tool, you can actually write a little bit of code and then get that work done. And all of this you can actually do with this scientific data that are multidimensional in nature. So you're not really processing only a single slice, you are processing multiple slices going through the stack or your dimension and getting the work done, right? So next time somebody bring you a problem with multidimensional data, and you might want to say how you can actually break it apart and put it together with using the existing tool, and you'll have a lot of fun with it. Okay, now that you have done all the work, you want to share it, right? What are the ways we can share it? We can share it as a map service, okay? And which means, you just make it available in the web, and it also supports WMS because some of you have to support these OGC standard, otherwise it's not kosher. So we support those. Map service will give you a pretty nice picture and you can do a bunch of stuff with it. However, if you want to do some kind of analysis and you need the pixel value and stuff like that, you have to use the image service, which also supports WMS, right? And then you want to process this thing as a service, then you can also create your geoprocessing service. So you wrote this fantastic tool, but you want people to use it from different places. You can actually publish it as a service, analytical service, and people can consume it, right? Publishing WMS on ArcGIS server is very easy. When you are publishing it, you just have to check this box. That's as simple as that. Then you will get a WMS service, right? You don't have to do any extra work to do this, right? What are the support we have in WMS? Now, one thing we did very silently, but very important thing for multidimensional data is we actually support multidimensional requests for WMS. What does that really mean? Earlier, when we have to, if you are publishing different layer in the atmosphere and altitude or different depth, you had to create different layer for it and publish all of them, and then somebody have to go turn on and off the depth that you're looking at, right? So it is kind of a cumbersome process. It took a long time to do this kind of thing. Now you can create one layer and publish it, and then you can send the query the way our slicing was working. Give me that slice, that time step, that time step, and your WMS request will actually honor that. So you have the get capability, get map, and then get feature info, and you can find all the dimensions that are supported, what are the value, and you can send the request. It will give you back that slice, right? So that is very powerful, and that simplified a lot of workflow for many organizations, right? Now, once you actually do this kind of thing, we want to serve that data for other people to consume, right? Whether we do it and in our Living Atlas, or you as an organization want to do it, so different people are doing it, right? Some of the example of doing that is like Modest data. Those are exposed as a service. We have live NOAA wind service. We have NASA global GLDS service, which shows soil moisture, evaporation, snowpack, and many more. The point here is that you don't have to keep this data locked on your computer. You can actually publish it as a service, and actually other people can consume it, display it, and do other stuff with it, right? And here's an example of that data is actually consumed in a viewer application. So you can view this data and consume it in ArcGIS Desktop Pro and server, your web map viewer, web application. You can write story map about it, and you can actually create an operational dashboard to manage your work and the organizational work. But when you publish, you actually enable WMS. Some other third-party application can consume it also. Here's an example. The WMS service is actually consumed in Dapple Earth Explorer, right? So, if somebody else writing the application, if you just, support WMS, they can consume it too. With that, I'll hand over to Deng to show you another demo.
Thank you, Norman. In the ingest demo, I have shown how to create a Mosaic dataset. And suppose I'm now an administrator of a server or an ArcGIS enterprise, or I'm a publisher. I want to share my scientific data with colleagues in my organization. So we can publish this scientific data to an image service or web image layer. Right-click on the Mosaic dataset, share as web layer. It's supposed to bring out this dialog of sharing. Okay, it's not working. Okay, here on this machine, it's bringing out that. If your server machine is the same as your publisher machine, you want to register the folder so that you don't have to copy all your data to the server machine. But if your publisher machine and your server machine are different, you want to copy all the data there. And you want to give a summary and tags. For configuration, you can select WCS so that your image service can be consumed by third-party software. After that, you want to analyze this, and it will give out some warning messages, such as your Mosaic dataset is not analyzed. But I decide to ignore this. So then you can click Publish to share this Mosaic dataset. You can also use Python script to automate this process. If you go to the help doc of ArcGIS Enterprise, you will see this example of publishing an image service from a folder of images. The first part is the same as manage scientific data by creating a mosaic and adding all rasters into the mosaic. And then for the publishing part, first you want to create a service definition draft. And then you analyze the service definition draft. After that, you stage and upload the service. Then you can publish, then your service will be published. So this is in ArcGIS Enterprise. These ArcPy functions are available in 10.6 or other versions. In Pro, you actually have similar things, but the syntax or the function name could be slightly different. So if you want to publish image service using Pro Python, you want to check out the help doc. There's another way of actually in Pro Python to publish this using Python, which is ArcGIS API for Python. They have these functions to publish the service definition and upload them into your enterprise. This is a slightly different workflow. So here, after you share with your scientific data with your colleagues, some of your colleagues may want to use the image service to do some analysis of their own. For example, I want to create contours of this HiCom data. So currently, it's showing the HiCom image service. It's actually showing the surface elevation. So you can use any of our spatial analysis tools that takes a raster as input to do the analysis. So for contour, you can input the HiCom image server layer and then specify some input parameters, for example, the contour interval, the base contour, and then run this tool. For the results, you can see the contour lines are nicely created. For image service layer, since it also have the time dimension, you actually can go to a different time step to create the contours for that particular time step. And for if these variables have depth dimension, the range slider will work too. That's how we share, how we consume scientific data by doing analysis. For in the real world, we are also consuming those image services by using them in web map and create your customized web app. Back to you, Norman.
Thank you, Dang. Okay, so we not only shared the data, by publishing as a service, it actually started, we went back to the cycle again where we start to ingest it. So not the data, but the service, and then we can view it, we can actually analyze it, right? So we can go on and the circle. This is a great way to create a scientific platform where people are putting their data together, sharing with somebody, performing analysis, for sharing the result. Somebody else is actually picking it up from the other end and actually doing some more analysis with it. So you can see that, currently in ArcGIS platform, we can do all of it, right? So going back and thinking, some of the stuff that you have to think when you are working with this data, right? This kind of data. When you're writing this data, write in the right format and embrace the common data model, because they all have all the standards and you have to follow the standards, otherwise, we won't be able to read it, right? And use data and metadata standards that is specified in CF and OGC, otherwise, again, it's like we won't have a roadmap for us to read that data correctly. When you are writing new data, if you are an organization, part of an organization and responsible for creating this kind of data, please produce an UCF compliant data. Otherwise, people will have difficulty, everybody will have difficulty, right? And if you have any intention to use this data in a GIS system, make your data spatial by specifying geographic or a projected coordinate system. Otherwise, you cannot overlay with this data with other data, and if you want to combine this data with other geospatial data to perform analysis, do impact assessment, do anything, you can do that, right? So that's very important, right? And you can use all of our tools to do your analysis. Where you cannot do it because you want to do your own algorithm or do something else, write your own sample tool, right? Script tool. That's not very difficult. And when nothing is working and you still want to come back to us and say, hey, how come you guys don't do that? Please tell us, clearly define your workflow, tell us what you need, and we'll try to do something about it. Okay? Thank you very much. Is there any question? If you have any question, I have a few more minutes I can take. Yes, sir.
Thank you, sir. I'm wondering what's the difference between WCS service and your Analytical service?
What is the difference between WCS service and our image service? That's a really difficult question. The image service is our proprietary service, right? And WCS service is the OGC standard. And so other than that, the image service by itself actually provide all the pixel value, and it has other property, and it has actually, we have a series of API that you can use to interact with this service, right? And when we publish that service, we actually enable the WCS service, right? So that it can, you can get the information through those protocols or through the standard. But is there any, if there is any underlying big differences, I'm not aware of, but if you can come to our island, I'll actually get you in touch with the other people who can actually elaborate on that OGC standard, okay? Any question? Okay, guys, go have fun. Thanks.